Hello everyone, welcome to this lecture number 8 of this unit, finite element and method. In this lecture we are going to see the development of the Truss equations. Okay, so this is Mr. Suyog Patil, assistant professor in Department of Mechanical Engineering, Sharad Institute of Technology, College of Engineering. Okay, today we are going to see the development of the Truss equations. So that means here in this lecture we are going to see the elemental stiffness equations for the truss, the displacement equations, okay, then strain and stress equations, elemental stress equations for the truss elements. So first of all we will see what is meant by truss. Okay, so here truss is an engineering structure made up of a number of bars connected by means of welded joints or bolted joints, riveted or sometimes pins also used to join these members. So this is an example we can see here. This is the bridge, okay, which is built on this river, and this bridge consists of number of elements. So this is the one element, this is the second element, this is the third element, fourth, then again fifth, sixth, seventh, eighth. Likewise number of elements are used, and this rigid structure is built here. Okay, this whole rigid structure is nothing but the truss. Okay, then again we can see here in engineering, truss is a structure that consists of two force members only. Okay, now this truss consists of two force members only. Either this truss will carry a tensile load or it may carry a compressive load. Okay, the only two force members will be there, where the members are organized so that the assemblage as a whole behaves like a single object. Okay, this whole assembly can behave like a single object. This bridge will consist a single object here, and this is the second example. It is the rooftop of this building. Okay, here also number of elements are connected and this structure is formed, and this whole structure it is called as truss. Now, assumptions. Now there are few assumptions that we have to consider while developing these truss equations. Okay, or again we can say while analyzing this truss member, this truss, again we have to assume some assumptions. Okay, and these assumptions are, so first one, it is all the members of this truss are connected together at their ends by frictionless pin joints only. Okay, so here we can say this is the truss. This is the first member, second member, this is the third member, and these three members are connected at this joint. Okay, and these are connected by means of a frictionless pin joints only. Okay, these frictionless pin joints are used to connect these members here. So now these two members are connected at this point, and again these three members are connected at this point. Okay, by frictionless pin joints. This is the first assumption. Second assumption is that a truss is a two force member. Okay, here we can say this truss is a two force member, that is each of the member is subjected to either tension or compression. Okay, now here we can see this is the first member. Okay, it is under compression. Okay, so this truss consists number of members, and these members are either in tension or in compression. Tensile or compressive kind of the loads will be there only. Okay, so this is the second assumption. Then third assumption is that in truss the loads are always assumed to be applied at the joints. Okay, all the loads are assumed to be applied at the joints only, at this point or at this point or at this point or at this point. Okay, these are the nodes. Okay, joints. So therefore all these forces will be applied at the joints only. Okay, here fixed joint, roller support is fixed support, roller support is there, and F load is applied at this joint. Okay, so all the loads are always assumed to be at the joints. Now these are the few assumptions that we have to assume while analyzing these truss members. Now we will see first of all the displacement vectors. Okay, now we can see this is a first member of the truss. Okay, first member, and it is connected. There are two nodes, node number 1 and this is the node number 2. Okay, node number 1 and node number 2 are the two nodes of this element. Now in local coordinate system, there are two coordinate system as we seen in the previous lecture, that is local coordinate system and global coordinate system. Okay, so this local coordinate system has 1 degree of freedom and this global coordinate system has 2 degrees of freedom. Okay, so therefore in this local coordinate system, so displacement along this x direction, okay, displacement of this element or bar member along the x direction is q1 at the node 1. Okay, and displacement of this member at node 2, it is q2 to q2 dash. Okay, q1 dash and q2 dash are the two displacements at node 1 and node 2. Okay, so here we can see, let us q1 and q2 dash be the displacement of the node 1 and node 2 with respect to the local coordinate system. Okay, in this local coordinate system, so therefore this displacement equations or displacement matrix, we can see this displacement vector in local coordinate system is given by this q dash is equals to this q1 dash and q2 dash. Okay, this displacement matrix q1 dash and q2 dash, this is the displacement matrix in local coordinate system. Okay, now here we can say in global coordinate system, so there are 2 degrees of freedom. Either this member will, when this member displaces from this position to some another position, here we can say this is the member which is displaced from this position to this position. Okay, so this node 1 will displaced from this position to this position, and this node 2 is also displaced from this position to this position. Okay, so therefore in this global coordinate system, so there are 2 degrees of freedom, and again we can say there are two displacement vectors x and along y directions. Okay, so therefore displacement of this node 1 along the x direction is q1 and along y direction it is q2. Here we can see q1 and q2 are the displacement of this node 1 along x and y direction. Similarly, q3 and q4 are the displacements along x and y direction, displacement of the node 2. Okay, displacement of the node 2 along x and y directions here. Okay, now we can see again in the here. Now in this first case, in local coordinate system, displacement q dash is equals to displacement vector q dash is equals to q1 dash q2 dash. This is the displacement matrix in local coordinate system. But in global coordinate system, we will see the relation between this local and global coordinate system here. So therefore, okay, here we can see this point 1 or this node 1 is displaced from this point to this point. Okay, so therefore it is displaced in global coordinate system by q1 here along the x direction. Okay, along x direction this is the q1, and along y direction it is q2. Okay, this is the q2 from this point to this point, it is displaced along y direction, it is q2 displacement. Similarly, so this point 2 or node 2 is displaced along x direction by amount of q3 here. Okay, so here we can see from this to this it is q3, and it is displaced in y direction by amount of q4. Okay, so therefore this distance is q4 here. Okay, along y direction. Now we again we have to calculate this in local relation between this global coordinate system and local coordinate system. Okay, so this is the q1 dash. Okay, in local coordinate system this point 1 is displaced from this point to this point by q1 dash, and this node 2 is also displaced from this point to this point by amount of this q2 dash. Okay, in local coordinate system. So now again we will assume this angle is theta. Okay, we will assume this angle is theta, and when we draw a perpendicular line here, okay, along this element perpendicular line, and by considering this triangle, okay, by assuming this triangle, right angle triangle, we will calculate this. Okay, this distance. So this distance is equals to, as this is angle theta, so cos theta is equals to this distance divided by this q1. Okay, this q1. So therefore this is equals to this q1 into cos of theta, q1 into cos of theta. Okay, this distance is equals to q1 into cos of theta. Now again when we extend this line, okay, so this angle will be the 90 degree. Okay, and this angle is the theta here. So therefore, so again from this right angle triangle here we can see this is this distance, that means this distance is equals to q2 into sine of theta. Okay, this q2 into sine of theta will be this distance. Okay, now this total distance q1 dash is equals to this q1 cos theta plus q2 sin theta, this q2 sin theta. Okay, this q1 dash is equals to, so therefore similarly here again also this angle is again theta, same angle is there, and this q3 and q4 are there. So therefore this q2 dash is equals to this q3 cos of theta plus this distance, that is q4 of sine of theta, q4 into sine of theta. Okay, then from this figure when we write these two equations, that means this q1 dash is equals to q1 cos theta plus q2 sin theta, q1 dash is equals to q1 cos theta plus q2 sin theta, and from this it is q2 dash is equals to q3 cos theta plus q4 into sine of theta. Okay, these are the two equations we can write down from this figure. Okay, then again when, or again we will assume this cos of theta is equals to L and this sine of theta is equals to m, small m. Okay, small l and small m, and these small l and m are the direction cosines. Okay, these are the direction cosines. So therefore these equations will be, so therefore q1 dash is equals to this q1 into cos of theta, that means L is equals to cos of theta, so therefore q1 into L plus this q2 into, instead of this sine of theta we will write m. Okay, so therefore q2 into m. Similarly this equation will be q2 dash is equals to q3 into L plus q4 into m, q4 into m. Okay, these two equations. Now again by again these two equations can be written in the matrix form. Okay, in the matrix form. So therefore above these two equations can be written in the matrix form. The q1 dash this and q2 dash, q1 dash and q2 dash is equals to this L q1 into q2, q1 plus q2 into m plus 0 into q3 plus 0 into q4. Okay, so therefore this will be written in the matrix form L m 0 and 0. Okay, in this second equation q1 and q2, uh, the coordinates of q1 and q2 are 0 here. Okay, so therefore 0 0, then q3 into L, so here L will come, q4 into m, so here m is there, and into this matrix, displacement matrix, q1 q2 q3 and q4. Okay, when we multiply these two matrices we will get these two equations. Okay, now again, now therefore this displacement matrix q1 and q1 dash and q2 dash, so this q dash is equals to, this is this is assumed as capital L and this is assumed as q. Okay, so here we can see this q dash is equals to L into q. Okay, this matrix is written in the equation, generalized equation. So where this L is equals to this L m 0 0 0 0 L and m. Okay, and this matrix is called as transformation matrix. This L matrix is called as transformation matrix. Okay, now we will see again in detail here. Now when we calculate this displacement matrices in, this is in local and global coordinate system. Okay, the relation between this local and global coordinate system. Okay, next we have to calculate here the direction cosines L and M and the length of the bar element. Okay, so therefore to find this distance, sorry, direction cosines L and M and the effective length of the element, that is LE. Okay, here, so this is the length of the element LE, then this angle is theta, the coordinate of this first node is x1 and y1 and the coordinates of this second node is x2 and y2. Okay, x2 and y2. So therefore this vertical distance will be this y2 minus this y1. Okay, y2 minus y1 is the vertical distance, this, and this horizontal distance will be this x2, this x2, this minus this x1. Okay, x2 minus x1, this horizontal distance. So therefore again from this triangle right angle triangle, this cos of theta is equals to this x2 minus x1 divided by this LE. Okay, x2 minus x1 divided by LE. Here we can see cos of theta is equals to, but this cos of theta is assumed as L. Okay, which is equals to x2 minus x1 divided by LE. Okay, and sine of theta, from this triangle sine of theta is equals to this y2 minus y1 divided by this LE. Okay, but sine of theta is equals to again m, so sine of theta is equals to small m is equals to this y2 minus y1 divided by this LE. Okay, now from this, okay, now again from the Pythagoras theorem, this LE square is equals to this x2 minus x1 square plus this y2 minus y1 square. Okay, so therefore this effective length of the element LE is equals to the square root of this x2 minus x1 square plus y2 minus y1 square. Pythagoras theorem is used here to calculate this length, effective length of the element. Okay, now here what we are going to do, here we are going to calculate the elemental equation for the truss members. Okay, elemental equation for the truss member. So this in local coordinate system, this truss is assumed to be 1D bar element. Okay, now by considering this 1D bar element and in local coordinate system, and again the elemental equation or elemental stiffness matrix for 1D bar element is the k dash is equals to a into E divided by LE, length of the element, into 1 minus 1 minus 1 1. Okay, already we seen this stiffness matrix in 1D bar element. Okay, now this is the elemental stiffness matrix for the element or for the member in local coordinate system. Okay, in local coordinate system, similarly we have to calculate this stiffness matrix in global coordinate system as well, as so that we will see here. Now, elemental strain energy for the truss element, okay, in local coordinate system is here. We can see this is the strain energy U is equals to 1/2 of the displacement matrix Q1 dash transpose into K dash, that is elemental stiffness matrix, and this Q1 dash. Okay, this is the strain energy for truss element in local coordinate system. This is equation number 1. Okay, similarly as we seen in the previous slide, so this q1 dash is equals to this L into Q. Okay, that means this transformation matrix L into Q is the displacement matrix in global coordinate system. Okay, so therefore by substituting this in equation number 1, we can solve this U is equals to 1/2 of this, instead of this Q1 dash transpose L into Q transpose into this K dash into this Q dash. Okay, that means L into Q. Okay, now again by simplifying this equation, so we will get this U is equals to 1/2 of this Q transpose into this L transpose into K dash into this L. Okay, and into this separately Q here. Okay, now this is the equation number 2 after simplifying. Now by comparing this equation number 1 and equation number 2, so we can see this is the equation of this strain energy in local coordinate system, and this is the equation in strain energy in global coordinate system. When we compare these two equations, so that we will get, instead of, we will get this K dash is equals to this bracket, that means this L transpose into K dash into L, capital L. Okay, so therefore this K is equals to, so this L transpose into K dash into L. Okay, and where this K is nothing but the elemental stiffness matrix. Okay, this K is nothing but the elemental stiffness matrix in global coordinate system. So therefore this L is equals to, but as we know this L is equals to Lm 0000 Lm. Okay, so L transpose will be this, we have to just replace this row into column. Okay, therefore this Lm 00 here will be Lm 00, then 00 Lm 00 Lm. Okay, transpose matrix is equals to convert row into column. Okay, now this is the L and L transpose, so therefore L transpose into K. Okay, here L transpose equals to this m0 0 0 0 lm into this k matrix. Okay, so therefore k is nothing but the ae by l, 1 minus 1 minus 1 1. Okay, now this ae by 1 ae by l is taken common, it is outside. Okay, and multiplied by these two matrices. Okay, so that we will get this l into 1, that is l, plus 0 into minus 1, it is 0, so therefore it is l here. Okay, now in the second term, this 0 into minus 1 is, sorry, l into minus 1 is minus l, plus 0 into 1 is 0, so therefore it is minus l here. Okay, similarly by multiplying all these elements, so that we will get this l transpose into k dash matrix is equals to ae by le into this l minus l, m minus m minus l l minus m m. Okay, this matrix. Now again by multiplying by this l dash in, sorry, l transpose into k dash into l. Okay, here we can see l transpose into k dash into l. So this ae by le and into this matrix and into this l matrix. Okay, l matrix. Again by multiplying these two matrices, so that we will get this k vector. Okay, so therefore this l transpose into k dash into l is equals to k stiffness matrix. K is equals to a into e divided by this le into this matrix. So therefore this l into this l square plus minus l into 0 is 0. Okay, so therefore this l square here, first term will be l square here. Now this second term, so this l into this m, okay, that is lm, plus minus l into 0 0, so therefore this second term will be lm. Okay, now third term, this l into 0 is 0. Okay, plus minus l into l, that is l square. Okay, so therefore here third term will be minus l square. Similarly fourth term will be l into 0 is 0, minus l into m is minus lm. Okay, now similarly second, this second row, this m into l is lm, plus minus m into 0 is 0, so therefore this second term will be lm. Similarly m into m is m square minus 0, so m square. In this way, by multiplying these two matrices, when we will get this k matrix. Okay, so therefore this k stiffness matrix k is equals to ae by le into in bracket this l square lm minus l square minus lm lm m square minus lm minus m square minus l square lm, sorry, minus lm, then l square lm minus lm minus m square lm n2, sorry, n m square. Okay, this equation, and this equation is called as stiffness matrix equation. Okay, now after calculating this stiffness, elemental stiffness matrix, we have to calculate the stress matrix. Okay, elemental stress matrix. So therefore this truss is in the local coordinate system, and it is assumed in the local coordinate system, and it is equivalent to 1D bar element. Okay, therefore this stress sigma is equal to this Young's modulus capital E into strain. Okay, strain into Young's modulus. So therefore this sigma is equals to capital E into this strain is q2 dash minus q1 dash divided by length of the bar LE. Okay, when then again by we will write this equation into a matrix form. Okay, so therefore sigma is equals to capital E divided by this LE into this minus 1 plus minus 1 1 and q1 dash q2 dash. Okay, this equation is converted into the matrix form. So this is the stiffness, sorry, stress matrix. Okay, elemental stress matrix in local coordinate system. But similarly in global coordinate system, this stress sigma is equal to E by LE, this minus 1 1 into this L matrix, transpose matrix. Okay, L M 0 0 0 0 L M, and this Q matrix, displacement matrix Q1 Q2 Q3 and Q4. So therefore again by multiplying these two matrices minus 1 1 and this matrix. Okay, so it will come minus 1 into L minus L plus 0, so therefore this minus L, similarly minus M L and M. Okay, this matrix into this Q matrix here. So this is the equation for stress, elemental stress in the truss element. Okay, in the truss. Now here in this video we have seen the elemental equation for displacement in local coordinate system as well as in global coordinate system, then stiffness matrix in local as well as in global coordinate system, and equations for the stress, okay, in local coordinate system and in global coordinate system. Friends, thanks for watching this video. If you like this video, please share, comment and like this video, then subscribe to my YouTube channel and click on the bell icon to get notified for more videos on this CAD/CAM subject. And thanks for watching. Thank you so much.